Let's see if we can apply our newfound knowledge of statistics and our ability in MATLAB to display the statistics and do some computations to see if we can solve a useful problem. So in communications, if I'm sending you data, ones and zeros, let's say, they're probably coming across as some voltage level or some frequency shift. A lot of different ways it can be, but it's going across a channel, and what you receive is not what you sent. You send say minus 10 volts and plus 10 volts, and what you receive is something around minus 10 volts and something around plus 10 volts. And the reason you don't receive the exact same value that you sent is because there's noise on the channel, and that noise is typically random normal noise. And so here's a bit rate. Okay, so here I'm sending. I'm going to say, okay, I'm going to send you a 0. That's going to be minus 5 volts, and I'm going to send you a 1, and that's going to be 5 volts. I'm going to assume for the moment that there's as many zeros as there is ones, and so when I send you a minus 5 volts, you get some normal function that you may get 1 volt, minus 1 volt, or minus 3 volts. You might get minus 15 volts, but you're going to get something around minus 5 volts, and minus 5 volts is probably going to be the mean, assuming it's not biased, and the distribution, how wide this is going to depend on the standard deviation of the noise. Same thing if I send you a 1, I'm going to send you plus 5 volts, and what you're going to receive is something from minus 5 volts to say 15 volts, and you're going to have to decide on the receiving end what whether that was a 1 or a 0. And so you can argue with yourself a little bit if you like, but basically it boils down to if this area is equal to this area, then that's about the best decision I can make, right? Because since these standard deviations are the same and they're the same number of bits one way or the other, when this area of underneath the blue curve from 0 to whatever is equal to this area, then that's going to be the appropriate decision point. So I'm going to say that 0 is my decision point, and if I send a 1 and I get a value that's less than 0, I'm going to call that an error. That's an error. A 1 was sent and a 0 received. And then if I come over here, if I send a 0, this area right here is going to be an error where 0 is sent and 1 is received. And so we can compute what the bit error rate is by computing these two probabilities. So the decision point, like I said, is set. In this case, it's midway between the two, since the standard deviations are the same, and the bit rates, the probability of a 1 or a 0 is the same. So if that's the case, then the probability of an error is the probability that a 0 was sent and a 1 was received divided by 2, plus the probability that a 1 was sent and a 0 was received divided by 2, and that's the bit error rate. And of course, this assumes that you send the same number of zeros and ones. So again, here we have we've set our decision point to 0. We have our 1s and our 0s, and we calculate these two areas. We add them up, divide by 2, and that's going to be our bit error rate. So I'm going to let you do one of these at home for homework, and you can generate this plot, and you can actually calculate this area and this area, divide them by 2, and add them up to determine what the bit error rate is. And then, of course, we have the norm PDF and the ERF and the ERF-C functions, and so we can use those as well then to determine what those are. So what I'd like you to do for homework is compute the bit error rate if a 0 is minus 5 and a 1 is plus 5 and the standard deviation is 3, and half the bits are 1s and half the bits are 0. So what you do is you generate 100,000 bits of each type, and then you can just see, for the zeros, how many of those bits turn out on the receiving end to be greater than 0, and divide that by the total number of 0 bits, that is the red ones. That'll give you the probability that a 0 was sent but a 1 was received. And then do the same thing for the blues. So for the blues, you take the total number of blues, you divide that into the number of blues that are less than 0. That'll give you the probability that the blue bit was sent. And you take those two and you average them, and that will give you the bit error rate. So, like I say, you can do that numerically from the data that you've generated, and you can plot the data, as you see over here. And then you can do it analytically, and you can use the norm PDF, the ERF, or the ERF-C for that. So that'll be your homework. Hope you have fun doing it, and wish you the best of luck.